Okay, then let's get started. Good. So good morning, good afternoon, or good evening, depending on the location. I'm Koji Yamashita, the moderator of today's webinar from UC Riverside. Welcome to the IEEE Foothill section webinar. Our Foothill section spans a wide geographical area stretching from West Covina to the eastern edge of California and from Temecula to Baker. Today, we are honored to welcome Dr. Panayotis Papadopoulos from the United Kingdom, who is the Associate Professor in the Department of Electrical and Electronic Engineering at the University of Manchester and the UKRI Future Leader Fellow. Thank you for joining us, Panos. Before we begin the presentation, please allow me to briefly introduce our speaker. Dr. Panayotis Papadopoulos received the diploma in engineering and PhD degrees from the Department of Electrical and Computer Engineering at Aristotle University of Thessaloniki in 2007 and 2014, respectively. His research focuses on the power system stability and dynamics, particularly under the uncertainty introduced by new energy technologies, as well as the application of machine learning in power systems. Dr. Papadopoulos has authored around 100 publications and works closely with industry leaders such as National Grid UK, Hitachi Energy, and so forth. He currently serves as the Technical Program Chair for the IEEE PES Power System Dynamic Performance PSDP Committee and has received several recognitions, including the Outstanding Engineer Award from the IEEE PES UK and Ireland chapter. So, Panos, the floor is yours.
Thank you. Thanks a lot, Koji. Thank you very much for the invitation. Thank you very much for the introduction as well. I very much appreciate the opportunity here. I will be talking today about small signal stability or instability in power systems dominated by converters. A lot of this work has been basically done by my team as well, and I'd like to thank Luke Benedetti also, who is to a large extent responsible for a lot of the things that I'll be talking about. Let me just provide a little bit of an overview first. One of the big challenges that power systems are facing these days is basically we're going through significant changes, and these changes are motivated a lot by drivers for decarbonization. And what that means is effectively we are introducing a new number of technologies. We have more renewable generation like wind or solar PVs, depending on where we are in the world. We have a HVDC, high voltage DC links, interconnectors. We have electric vehicles also, batteries, and heat pumps also to electrify heat in different parts of the world. Here in the UK, for example, it's quite common. And all of these new technologies, effectively, they are driven to a large extent by achieving decarbonization target, but also to achieve for other, let's say, technical, economic, and also social reasons as well. So all of these, in a nutshell, introduce what I like to call added complexity to an already very complex system, and added uncertainty as well. Complexity because they have very different dynamic behavior, and this is governed by control to a very large extent. And uncertainty because of the intermittent nature for a lot of those sources, but also because of the human behavior of how we will be using energy effectively in a more electrified world. Like, for example, how will we be charging our electric vehicles? And what I'm mostly interested, myself and my team, is around the challenge related to stability and dynamics of the power systems. And the bottom line is that if we don't get this right, we might get blackouts. That's the worst case scenario that we get out of that. So power systems, we know that they are dynamic, nonlinear, complex systems, arguably amongst the most complex man-made systems. And what we do here to represent this dynamic behavior is we use hundreds or thousands of differential equations to represent the dynamic behavior of the system. And this is, we can solve these equations by using numerical integration methods or the so-called simulations, but the timescales can vary a lot. They range from less than milliseconds up to tens of seconds. And this is a very, very computationally intensive process, especially if we're going to do this in operational timescales. And the increasing complexity that I talked about comes to a very large extent by this very different dynamic behavior of all these new technologies that we are integrating. They are high in number as well. They are mostly connected via converters, via power electronic converters, and they have much faster dynamic phenomena. They are to a very large extent governed by control, and they also introduce strong nonlinearities like limiters or discrete control changes and so on, which makes our lives a little bit more tough in terms of the computational aspect. Now, the increasing uncertainty comes to a large extent also from this very high number of devices. We have now millions of devices like solar photovoltaic farms, for example. And if we want to exhaustively do analysis, we have a huge search space of possible operating conditions. And now we have dynamics basically becoming increasingly important because of these challenges. Now, what is already happening, what we see in the system, in power systems, is that we start observing new types of dynamic phenomena that we don't really or fully understand yet. So we understand that we need to be able to characterize these mechanisms of instability a bit more concretely. We want to understand how these types of instability or these oscillatory phenomena, if you will, behave across a range of operating conditions. And we want to be able to have proper models and modeling frameworks to represent these behaviors. We used to use, for example, the so-called RMS or root mean square simulations or phasor simulations, if you will, but we are now considering going into the much more detailed EMT or electromagnetic transient domain. Our potential approaches that sit somewhere in the middle, like hybrid modeling or co-simulation approaches and so on. And as I mentioned, so we've already started seeing these new types of dynamic phenomena in various parts of the world. In the US, there have been observed oscillations like that in Canada, in Australia, and also here in the UK, specifically in Scotland, where I used to be in the past few years, where we have these 8 Hz oscillations. And we need to get this fundamental understanding, so understand under what conditions these phenomena appear, in which locations, and what devices participate in them. And of course, the bottom line is, how do we mitigate them? Do we apply some kind of a damping control, or do we change discrete control modes, like, for example, have a bespoke control mode for a weak grid operation? Or do we install synchronous compensators like spinning masses effectively? Or do we impose operational constraints and come up with some kind of a stability service and a market-based approach? So these are all open questions. And of course, we shouldn't forget what these complex dynamics do to the traditional aspects of power system stability, which you might have heard of, related to the angles, to transient stability, related to voltage and frequency as well. So similar challenges also come from the distribution side now, because we have these so-called active distribution networks. And things are a little bit challenging also there, because we usually have less situational awareness, and we usually treat distribution networks as a lumped entity in a sense. So it's quite difficult to understand how the dynamics from distribution networks can actually affect transmission. And we have also changes coming from the load side, not just from the generator in the form of solar PVs or wind farms that I mentioned, but we also have electric vehicles, and very recently there's a big discussion about data centers as well, which are causing changes to the dynamics of the load as well. Now, a lot of the work that my team and myself are doing are around basically this defining again, or redefining, if you will, dynamic security assessment. So how can we deal with this complexity and uncertainty? Can we capture these detailed dynamic behaviors and improve monitoring, situational awareness, and control? And this is to a very large extent means that from one perspective, we need to have these appropriate models and simulation frameworks to understand these new dynamic phenomena. And from the other point of view, we can also use data-driven methods, so measurement-based methods or machine learning-based methods that can help us with capturing this detail, but with very fast time scales, which can enable this enhanced monitoring and situational awareness. And of course, we're very much interested in proof of concept applications. To this end, these are some the little icons that you see around here are some of the people that in one form or the other I'm interacting with while going in this journey. And a lot of my research is effectively funded by the Research Councils of the UK, so UKRI. But very recently, I'm very excited to say that we also became finalists for what is called a Manchester Prize. So this is some funding that we got from the Department for Science, Innovation and Technology here in the UK. And this is effectively exactly what will help us build this proof of concept application. So take research one step closer to real world applications effectively. Right. So I'm going to start going a little bit now into the more technical part of the talk. So I'm going to scan through a few different areas. I'll try to provide some detail, but I'll try to keep it at high level at the same time. So at the end of it, feel free to ask any questions you have or also get in touch with me for any questions you might have. So first of all, let's talk about characterizing these new types of dynamic phenomena. So the first thing that we started doing while looking in this area, so we said, okay, let's look first at what we call small signal dynamics. So effectively, dynamics are affected by small disturbances. And that means that we can work with linear models or linearized models even better. And all our analysis is valid around a small region around an operating point. So if the operating point changes, this behavior might change. They're very useful, these models, because we can get a very, very good understanding of these mechanisms. That's why we went in that direction. But they also have these limitations in terms of the small disturbances. So they are not useful effectively for capturing nonlinear dynamics related to very large disturbances, like short circuits, for example. And they cannot capture phenomena like limit cycles or hybrid dynamics, which I think can be very interesting and can cause potential challenges in future power systems with a lot of converters. So just a little bit of some basics from with respect to this small signal stability analysis or eigenanalysis as it is called. So we start with a so-called state space representation of the system, which is given in this form here, and you have these A, B, C, D matrices, which are effectively and this dx over dt, so these are the state variables, and this is effectively describing the set of differential equations that we use to represent a power system. And this is what I talked about earlier, that can be thousands of them even in very large systems. And then we linearize them, we use a Taylor approximation, and then after we get the linear model, we can calculate the eigenvalues, which come in this form, they are complex numbers, and then we can analyze stability of power systems through that way. If the real part of the eigenvalue is negative, system is stable. The closer it gets to the real valued axis, to the zero, then we start having poorly damped oscillations or potential problems of instability if it goes to positive. We can also calculate what we call eigenvectors using these equations here, the right-left eigenvectors and participation factors. And in a nutshell, these vectors, or well, effectively they are all vectors. So these vectors basically can help us understand which state variables affect particular oscillatory modes. So if we have a particular oscillation, we can actually pinpoint and say, well, this is the particular device that is participating in this oscillation, and this is the particular controller or part of the device that is actually responsible for that, so that we can go back and maybe retune our converters or do other actions to mitigate that. Now, we then started, after we decided that let's look at the small signal dynamics, and then we decided to basically, because in the literature you can see a wide variety or range of different models for converter-driven generators. And this GFM, GFL here stands for grid forming or grid following converters. And these are two of the, let's say, key categories of control architectures. Grid following is what we mostly, what we mostly have connected currently in power systems. They are the typical converters that have a phase-locked loop to follow the dynamics to measure the frequency effectively and follow the dynamics of the system dominated by synchronous generators. But with more and more converters, we need this approach of the grid forming ones, which can actually support and generate a voltage source effectively and behave very, very similarly to synchronous generators. So one of the most common approaches is what is called a virtual synchronous machine, which effectively is it's behaving like a synchronous machine, like the swing equation of a synchronous machine. And we started doing this case study here where we said, okay, let's take the typical control structures of these converters, grid following converters, and they can come in different flavors. And we chose some that you can see, that you can see here on this slide. Some of these blocks might be active or not, depending on different implementations available. And we did the same thing for grid forming converters. Here, things are not so clear. So because this is not very well standardized, because these are new technologies. But we still have some standard architectures coming up. And you can see here these different variations that can happen here on the block diagram. So we took all these converters and we took a case study. We built a small system, 2-machine system, as you can see here, and then a 3-machine system. And we ran different case studies based on different mixture of synchronous generators and grid following or grid forming converters in a lot of different setups, as you can see here. And basically, we did this eigenvalue analysis, this linear approach that I mentioned before. And we also looked at the effect of different parameters like the length of the transmission line or the loading of a system or penetration of generators. And what you can see here, so I won't go too much into the detail of this. These are all based on published papers that we have. So I have the links here. You can follow up on more details if you wish. But the bottom line is you can see here with the black and the red dots here that the eigenvalues can actually change quite a lot depending on which control architecture we decide to have. And we can also see that different types of oscillations can appear based on which type of control architecture again we have. And this can vary a lot, and this can also come so converters can actually come and interact with so-called electromechanical oscillations, which are linked to traditional synchronous machines. But we figured out that some of those grid-forming converters can actually interact with synchronous generators as well. We also did some sensitivity analysis based on different parameters that you can see here. So this is only the real part of the eigenvalue that I mentioned before, which effectively tells us, so whenever that is positive, this means that the system is unstable. So you can see for the different types of control architectures that you can follow, you can see that actually some of them for cases where the synchronous generators are quite small, they can actually cause instability here. So in systems with a very high penetration, for example, we might have some instabilities appearing here. And we did this a little bit more exhaustively also in a larger system. So all these black dots that you see here are effectively cases where instability has appeared. And we are changing the installed capacity of these grid forming converters or grid following converters. And we notice different potential modes, let's say, of instability. And some of them are real valued and then rely on synchronous machines. Some of them rely on the phase-locked loops of the grid following converters. Some of them are very high frequency phenomena, like more than 2 kilohertz. Some of them are in this subsynchronous range, which links more to some of those oscillations that we are actually observing in real power systems happening across the world, as I mentioned before. But the bottom line basically of this work is that it's very complicated, right? So we can, on a case by case, understand this phenomenon, these dynamics, but the problem is that it can be so dependent on the exact control structures, and it can be so dependent on the exact layout of the system that is very difficult to generalize and have one approach fits all. So from that, and based on some past work that I've been doing related to probabilistic studies, we thought, okay, let's then have a look and focus at how the changes of operating conditions can actually affect these new types of dynamic phenomena. And we came up with probabilistic framework. So basically what we wanted to do here is this is a typical day, 24 hours effectively, split in half-hour periods. And you can see how the wind would vary within the day and how with the solar PVs vary within the day and so on. This is just a typical day taken from data from the National Energy System Operator in the UK. And basically, we went through this wide range of operating conditions, and what we can see is that these modes can actually vary a lot. So these are examples of particular oscillatory modes, and this one is, for example, one that is of interest is in this subsynchronous oscillation range again, around 15 to 17 hertz. And we can see that as we are changing operating points, we can actually get a lot of cases which cross this zero here, which means the system becomes unstable for this particular subsynchronous oscillation mode. Now, different modes can behave very differently, as you can see. So we tried to formalize this a little bit more. So we did Monte Carlo analysis effectively, and we created this framework where we start from the characteristics of the system. We have a model of the system. Then we sample the probabilities, let's say for a day, as I mentioned before. We run an optimal power flow to mimic how the dispatch of a market would behave effectively here. And then after that, we effectively linearize, initialize our models, and then we perform eigenanalysis and a little bit of filtering and clustering. I'll talk a little bit more about that. And then we go to this part where we actually characterize these oscillatory modes through a range of indices and the processes that I will explain a little bit later. Now, this is just a visualization of how we sample the uncertainty. So you can basically sample randomly an operating point following Monte Carlo within the day, and then we add some Gaussian uncertainty around that, which can, depending on what is the actual uncertainty you are modeling, it can be also different. It doesn't have to be Gaussian necessarily. So you can do more fancy things with in terms of sampling probabilities. We also follow a clustering approach because we realize that after this Monte Carlo simulation approach, we have a huge number of modes to analyze. So if we want to get a little bit of a feeling of how these modes behave, we have to bulk them somehow or cluster them somehow. And we chose to do this here in our approach following this k-means approach where we cluster based on those participation factors. And that's interesting here because we don't cluster the modes on where they appear on the complex plane, but we cluster them on what states are actually causing them. So what mechanisms are actually causing them. So a cluster does not necessarily stay on a particular part of the complex plane, and I'll show some examples following on, but it actually tells us what states or what mechanisms are participating in that particular cluster. After we do this clustering approach, then for each one of those clusters, we can calculate what we call category participation factors. So effectively, we assign the states to some particular categories. And this is an example of how these categories can be defined based on what we believe is a physical interpretation or a physical meaning of the power system behind. Like, for example, you can define one category which says these are all the states related to the active power and frequency control of the power system, which can include active power controllers from converters. It can include the phase locked loop from converters, but it can also include the synchronous generator rotor dynamics or the governor of a synchronous generator. And similarly, you can have a reactive power and voltage category, which has automatic voltage regulators of synchronous machines, but at the same time has voltage control of converters as well. And we also came up with categories related to inner voltage controller and inner current controllers of converters and so on. So we can add all of those things together into categories. And after we've done that, we can calculate what we call a stability weighted participation index. So for each one of those categories, the participation of its categories, we just weight them based on how close to the stability boundary they are or not, to assign a different level of significance basically there. So something that is close to the stability boundary is effectively considered more important in our analysis because this is the mode of interest. This is the thing that we should be looking at. And we normalize also this so that if we add all the category participation factors, then they all add up to one. So effectively, it's a quite useful tool to analyze the behavior. And now we've done some studies here in a larger network, the 39 bus network in this particular case, the IEEE 39 bus one. And these are the converter controllers that we used for grid forming and grid following. And here are some of the results. So these are how the clusters look like that I talked about. And you can see, as I mentioned, that they are not necessarily concentrated. I mean, they can vary a lot, as you can see. This is because we cluster based on participation factors and not based on just where the clusters sit on the domain. And what this allows us to do after we calculate the stability weighted participation index as well, what this allows us to do is do effectively this analysis. So you can see the different clusters here. Let's take, for example, this cluster 7 that you can see here, right, the purple one. So cluster 7 is here. And what we can see is that, okay, this particular mode, this particular oscillation is coming from the inner voltage and inner current control loops, as you can see here, of grid forming converter number 7 and grid forming converter number 3. So we can actually pinpoint the oscillation responsible for this. And this is not based on just a single snapshot. That's the added benefit here of a single operating point, but it is actually across the entire range of possible operating points. So this shows us effectively how these modes, these clusters behave across a range of operating points. And exactly because we follow the probabilistic sampling approach, so we can actually calculate the probabilities of these clusters, right? So we can say, for example, what is the probability of this cluster 5 here, for example, to have a particular value in the stability boundary, in the real part of the eigenvalue. And you can see that some of those clusters do not appear in all cases, so we can even calculate the probability of one of those oscillations to actually appear over a range of operating conditions. This is some quite useful information here. And we can do also stuff like focusing on particular oscillatory behaviors, as you can see here. So this is a particular subsequence oscillation that I was talking about. And what we did here is we, following a realistic tuning approach, but we tuned the converter for different time constant from 7.5 to 10.4 milliseconds. And you can see how this specific mode going from black to red is actually becoming unstable when we reach this value of the 10.44 milliseconds of the time constant. And this is again following a realistic tuning approach, so this is something that could happen in a realistic setting. And then if we then get this value and we follow our probabilistic analysis, then we can actually find that there is, in reality, over the range of operating conditions, this is not necessarily to be unstable for all operating conditions, but for, if you calculate the probability here, for 69% of the cases, there is actually a probability of instability denoted by these positive values here on the right-hand side of this cumulative distribution function of the probability related to this particular mode. So this is a quite interesting tool here. Now, we also went a little bit one layer after more in depth and not just concentrated on we now have seen how the eigenvalues move, how the modes move effectively, and what mechanism is responsible for them. But we also wanted to ask the question, do the model properties change? Do these eigenvectors and participation factors themselves now change when we have more converters? And what are potential implications for stability and control following this approach? And again, we followed a very similar approach where we sampled a number of operating points. So these are the cases or the operating points that we actually sampled, if you see, following a similar approach that I mentioned about before, that I talked about before. And we now bumped into the issue of modal tracking. So we actually now realize that we need to track a particular mode, how it changes when the operating point changes. And this is not a trivial thing necessarily. And we needed to do that because we needed to track the mode first to then be able to say then how the modal properties of that mode have actually changed. And we followed an iterative process following this extended pole-weighted modal assurance criterion. You can see here on the right-hand side on the bottom. It's not important to go into the detail of that, but basically what this metric can tell us is give us a quantification of how much two different vectors differ from each other. And following an iterative process, we basically match each mode between operating points. And once we do this for a number, as you can see here in this figure, for a number of operating points, we have this metric here that tells us how the modal property has changed. And we basically pick the maximum value of that as a proxy number and say that's our metric of how we will quantify this variation. And then we apply these to test systems, and I won't go too much into the detail again of this. But what we figured out effectively is that indeed in systems with converters, actually you do have these modal properties tending to change more. And we've noticed this across a range of different frequencies as well. So we have these very low frequency, non-oscillatory modes included here, which are more closer to the electromechanical range. So typical oscillations that you would see also in a system with synchronous machines. We have some low frequency modes, which are again still the bottom of it. You do have you are close to this electromechanical range, but going a little bit higher to more converter-driven phenomena. And then we have some mid-frequency as well. This is in the subsynchronous oscillation range, and also some very high frequency phenomena. And we calculated the modal property changes, and we see if we have only synchronous machines, vs. if we have converters, actually the modal properties tend to change more with the converters. This doesn't apply in the very high frequency modes necessarily, and we have an indication that this might be linked to the closeness of the mode. So if you get multiple modes being close together, this might actually influence this metric. But I think we need to do a little bit more work in this direction. But how this thing would look like, so if we look at the participation factors, on the synchronous generator only system, we can see that they are quite, they don't change that much across different operating points. But with converters, they actually tend to vary a little bit more. And the same thing happens with left and right eigenvectors as well. And these can have some implications for control as well, right? So if we focus specifically on this particular mode of around 15 or 17 hertz that I talked about earlier, this mode can actually be destabilized if we change the closed loop time constant from 1.5 to 3.75 milliseconds in this particular case study here. And if we do calculate the modal properties, now for this particular mode, we actually saw that the variation was not that high. So this is good. It's a good thing because it can show us that we can have confidence when characterizing this particular oscillation using participation factors, because they don't vary that much over operating range. Right. And we also did some initial or very initial analysis related to damping controller design, where we have calculated residues. So again, I don't need to go too much into the detail of this, but basically there is a link because we design damping controllers a lot of the times based on residues. So these residues, how much they change across an operating range, can actually have implications on the effectiveness of the controllers as we change different operating conditions. And as a final part, I want to talk a little bit about the so-called system strength. So we Right. So we have a lot of metrics about what we call system strength, and a lot of those metrics are a lot of the times based on some kind of a static representation of a system based on a impedance at 50 hertz. And this usually tends to bulk together voltage and frequency. These metrics also don't necessarily take into account the dynamics of the system. So we thought about this, and we thought we should do something a bit more in that direction. There are approaches, some recent approaches, impedance-based approaches, effectively, which are actually do take into account the dynamics of the system a lot and link this system strength with the stability margins of the system, which are very, very, very useful. But we wanted to take a little bit of a different angle here and basically focus on, because system strength, to some extent in our mind, is linked to a weak system should have its state variables, like the voltage and the frequency, for example, let's say, should have these variables changing a lot, right? Being sensitive to changes. And in the small signal strength perspective, again, so just small signal, small disturbances, basically, we tried to come up with a metric that I will explain a little bit later. For let's say a given disturbance in one location, we wanted to see how would the change in voltages and frequency propagate throughout the rest of the network. So we have a small perturbation somewhere happening in the system. How would that affect the voltage and the frequency across an entire system? And this gives us this ability to decouple basically also the strength between voltage and frequency, which is quite important because it doesn't have to necessarily, and we have examples to show that as well, it doesn't have to be together. So a system could be strong in terms of voltage, but not necessarily in terms of frequency, for example. And we use that, we use the model responses effectively to do this process. This is just a typical example of, let's say, an oscillatory response. If you look at this dashed red line here, so if we decompose this to the different modes that it contains, you actually get the green, yellow, blue, and these solid red curves. So this is the decomposition of this aggregated response. What we wanted to define here is we wanted from each one of these model decompositions, we wanted to actually see, so what is the biggest deviation from each one of them? And we can actually do this analytically, because if we know that the response in time is effectively a damped sinusoid, which is what describes an oscillation, then we can actually analytically calculate what is the amplitude of this, what is the highest, the biggest amplitude here. And then we can take the maximum absolute value, like in this particular case, it would be this value for this green mode, effectively. And we can use that as a proxy metric to say, right, that's our analytic metric to say, this is the amount of variability we have in the system in this particular mode. Yeah, this is the green curve that I talked about. And yes, we validated this approach in a single machine infinite bus system. Things are straightforward because the analytical approximation, there's no approximation, it's actually a direct derivation. So it perfectly stands. But what is more interesting is if we go to a more complicated system like the Kundur two-area system here, and we have different case studies only with synchronous machines, with grid-forming converters, or with grid-following converters. And we replaced these machines effectively, G3 and G4, with converters. And what we could calculate here is, so this is the bus where we introduce a disturbance, and this is how this is actually propagating across the rest of the network. So these numbers here effectively correspond to the buses of the system, as you can see it from one side to the other. And you can see that actually this variability, how we have defined it, can be quite different with different, if we have synchronous machines. So you can see that, for example, change here is much more sensitive and causes state variables to vary across the system. But when you have grid following converters, the same thing does not necessarily apply. And also this top row here corresponds to delta omega, which is the frequency effectively. And the bottom is actually the voltage. So you can see that, again, frequency and voltage can be quite different in how these disturbances propagate across the system. And we can also pinpoint exact modes that are responsible for these variations, which is a quite interesting approach. So we can say, for example, that this variation that we just described is actually because of this mode or because of that mode, which are exact oscillations that we notice in systems. And just before I conclude, so following this entire process, so Luke Benedetti, who is a PhD student of mine, he actually had his Viva today. He came up, also he developed a tool, a small signal modeling tool, which we open sourced and made available. So you can download it and use it if you will. It's MATLAB based, so it has detailed converter models. All are linearized models, but you can have this modular approach where you can actually choose different control structures and build systems quite easily. It takes inputs also from MatPower, so it interacts with MatPower. And it's also automatic, so you can connect the models automatically, and you can also initialize the models automatically. So you have the ability to scan through this number of effectively thousands or tens of thousands of cases quite quickly. Yeah. So basically, that's it. That's my presentation from my side. And just to sum up a little bit what we talked about, and then I'm more than happy to answer questions if you have. We talked about this increasing complexity and uncertainty in power system dynamics. We have these new types of phenomena that we don't have the full fundamental understanding of how they behave, especially across a range of different conditions. We also talked a little bit about this idea of system strength and how we define it. We think that there is still work to be done in this direction and define this a bit more concretely. I also talked about the usefulness of probabilistic studies, which can actually reveal this behavior of oscillatory modes across ranges of operating conditions, and also give us information on how likely are oscillations to appear. Yeah, and we also talked about this idea of the small signal variability and the modal properties of converter driven or converter dominated systems and how they can tend to vary more. Yeah, so this is me. These are my contact details, and maybe one thing to note is also that I do have also one open PhD position in this area. So if anyone is interested, yeah, feel free to either spread the word to others or directly get in touch with me as well. I'm more than happy to discuss about that. So that's me.
Thank you for the nice presentation. Um, if you want to ask some questions, please utilize the chat window. There is a chat window, and you can type your questions if you have. And then, in the meantime, so I'm so impressed by this presentation for sure, and especially there are some like undergraduate students, and then they are not so familiar with the grid forming converters and then also grid following converters. And then in class, I emphasize that grid following converters are predominant at this stage. And then what is the current trend of the grid following converters? For example, can we purchase it right now? And what is, no, I think the percentage of the grid forming converter is very, very little. That is my understanding. But what is the current situation, for example, in the UK?
Yeah, so I agree with you, Cozy, entirely. So I think there are very probably no applications of grid forming or very, very, very limited. There definitely is are pilots that are happening. So
Mm,
I was involved. I wasn't the person leading this, but I was involved in some work at the University of Strathclyde where we effectively got some data from a pilot from a grid forming wind farm that was also shown to be able to black start a part of the system as well. There are some manufacturers that are actually testing this in real systems, in real wind farms effectively, but I'm not entirely sure that this is a product that someone can buy off the shelf and install a grid forming. Having said that, I think there are batteries that are grid forming,
mm,
which are ready-made products almost,
mm,
and there are potentially some HVDC links that have some form of a grid forming converter. Now, again, this is one of the challenges that I didn't highlight enough. A lot of these are behind proprietary black box models of the vendors, of the technology vendors. So it's very hard to be able to exactly say what happens, even for system operators that do have access to the models because they are black box, so you cannot see the equations inside. But I do have the feeling that some of the HVDC interconnectors might have this ability of grid forming.
Okay. Yeah, thank you for this explanation. And also, you are talking about the fraction of the grid following converters and grid forming converters in your case study. And have you ever thought about the connecting point? Like, you know, I think if we connect the grid forming converters to the transmission grid or distribution grid, and then the results can be different. That is my intuition. So have you ever tried that out in your study?
So you mean what if the connecting point was different effectively?
Yeah, the connecting point. So the one possibility is that the capacity is too large, and then we can connect that grid forming converters to the transmission grid or sub-transmission grid. That is one scenario. Another
Mhm,
scenario is that we connect the grid forming converters to the distribution grid. The hundreds of grid forming converters, but each capacity is relatively small,
mhm.
but the total
Yeah,
capacity is the same.
yeah, I see what you mean. Yeah. No, we don't explicitly go into that level of detail in our studies, but the point of connection side of things, I think it's very interesting. It is something that we should be, putting more attention at. In what sense? So, for example, in the study that I showed, where we were looking at this small signal variability effectively. So this is exactly the locational element to it, right? So if you connect in one point or a different point, you will have different behaviors. And if you have one type of controller, grid following, let's say, or grid forming, you will have different types of behaviors as well. So grid forming tends to be a little bit more, I mean, the solution or a bit more robust to problems related, for example, to the phase locked loop, because they don't usually have one, at least in normal operating conditions. Because sometimes when they go to fault right through, they might have. But this is effectively, yes, it's not going to be probably an issue for grid forming converters in such a case. Having said that, if you have multiple grid forming, as you said, if they behave like, for example, virtual synchronous machines, if that is the approach that someone follows, there is no guarantee that they might not interact together with them, between them. Sorry. In a
Mm.
similar sense that synchronous machines would interact if you put them close together, like intra-plant modes or inter-area even modes. So these are the things that I think we need to be investigated. And this is why we were saying that the complexity starts becoming so high that it's not one kind of like approach fits all. So we need to be
Mm.
careful when we are looking at the specific problems and be aware that, yes, we can solve one problem, but we need to be careful of not causing another as well at the same time.
Okay, thank you. And can you open the chat window? We have a few
Yeah.
questions on chat window.
Yes. So, I'm sorry, I'm clicking something. So the first one says if this material is available for, yeah, I'm happy to share the slides. Yes, don't, yeah. You can directly get in touch with me, or I can also send those to you, Koji, and you can distribute to people that ask. That's,
Yeah, in this case, I can post your slides to the IEEE Foothill section website
yeah,
because
that's perfect.
yeah, I usually put the historical recording videos on the our
Mhm,
website, so I can
mhm.
do
That's
that for
great.
you.
That's great. Perfect. Thanks a lot. Yeah. And there was another question if EN Phase, a US manufacturer, is using grid forming technology. I'm afraid I don't know about that. I don't know if you happen to know, Cozy, but I don't know the specific manufacturer.
Um, no, there is only like a demonstration project in Hawaii, as far as I know. Maybe somewhere in the US using battery systems, but I'm not so
Mhm,
familiar with this as well.
mhm, mhm,
Because mostly I spend my time in Japan. I heard that there is one like a grid forming converters made by one of the Japanese manufacturers, and they plan to install it in one of the small isolated island near Philippines in the future. So it's
mhm,
still, it is ongoing, and then
mhm,
they do not establish the technologies. So this is still, in infancy, like not matured yet.
mhm,
That's my
yes.
understanding. So
Yeah.
yeah, I don't know. Maybe I can check that out later on.
Mhm. Yeah, yeah, that's a yeah. So apologies, Roberto. We don't have a full answer. I don't have a full answer as well for you, but yeah, I think they are. I mean, I'm sure there are I'm very confident that a lot of manufacturers are developing them very actively and probably are very close to having ready products. I don't know to what extent these might have been deployed in real systems, to put it that way.
Yeah. And so we organized multiple webinars in the past, and one of the speakers from ERCOT, she told us that the grid forming converters can start with batteries, not the wind farm or the solar PVs. And I think that really makes sense to us. Do you agree with this?
Yeah, to a very large extent, yes. I did mention a project where they installed in wind farms as well, because
Oh,
wind farms do have some inertia, right? Because they still have a
uh,
spinning turbine. It's small inertia, but they do have some. And they actually showcase that you can get inertial response from slowing down the rotor of the wind farm as well, of the wind generator, sorry. Having said that, this is limited and you have to be careful how much you slow it down because you might go, I mean, if the speed decreases too much. So there are limits as well related to the mechanical side of things, if you will. Having said that, it's not impossible to do it, but yes, you are right. It makes a bit more sense to have some sort of energy store if you want to have inertial response. That is, if you want to have inertial response towards loss of generation, right? So for controlling over frequency, you can actually do that. It's fine. You can reduce the power output of converters quite quickly, and it's fine. It's not a problem. But to increase the power output of a solar photovoltaic, the only thing you can do this is if you keep operating outside of the maximum power point, and then you are just throwing energy, which doesn't make a lot of sense. So yeah, I agree with that. It makes a bit more sense with batteries. Having said
mm,
that, there are limited cases where you can actually get from wind rotors as well. Or, some people are thinking of potentially having maybe like a supercapacitor or a small battery even as a hybrid plant, if you will, to some extent. So a combination of a wind farm and a battery, for example.
okay. Thank you. Um, I don't see any more questions on this.
I don't see as well.
Okay. But anyway, yeah, that is really, impressive for me because, and also the small signal stability is really important in the future because we have already recognized such kind of like a high frequency oscillation event, um, like at a steady state condition. Of course, we must have like a kind of disturbance before that. But after that, we started to see the high frequency oscillations at a kind of like a post-disturbance steady state condition. So this work must be really critical, crucial in the future. So I really look forward to the future outcome.
Thank you, thank you. I think, yeah, I think this is one of the challenging problems that we face in power systems these days. And there are a lot of people in the world that are working in this area and looking into this phenomena. So every day we kind of like learn something new. So it's a quite active area.
Yeah, and also, without the measurement devices, probably we cannot recognize it, right? Because that's a high frequency oscillation. So if this oscillation happens in distribution grid, how we can realize it, how we can detect it? Probably,
Yeah,
the grid operators cannot know it. And then if, that such oscillation will oscillate the entire grid, a grid-wide oscillation, then the grid operators can recognize it.
yeah.
Or yeah, it's kind of big challenge, I feel.
I agree 100%. I think you hit right the spot there. So it's in my view, this is why a lot of our studies we focused on interactions basically. So where more than one, I mean, we looked at oscillations coming just from a single unit, of course, but we were interested in those cases where you have multiple units oscillating against each other, for example,
Mm,
because this is what is taking us to a situation where you might have not be n-1 secure, right? So if you lose one unit, I mean, what could happen if you have these oscillations? They are sustained, they might become unstable, or they start growing. Some unit might trip. If it's just the one unit tripping, it's not ideal. We don't want that, of course, but system usually is n-1 secure, so we will not get any blackout or anything like that. If you have multiple units though, and if you have this oscillation start growing and affecting more than one unit, then you go into a situation where you have n-2 or 3 or so on. And that is really, really a difficult situation because you might have more units falling off and potentially leading to load setting as well. And as you said, how much we see them, this is also quite interesting. So a lot of system operators throughout the world do have monitoring at transmission level, so we see them happening. At distribution, probably we don't have any idea. I think the only thing we would see is potentially the effect of them, because if again, if they appear and they are very or not very, but they are well damped and they don't cause any disruption, we might not know they even existed. And to some extent, oscillatory responses in power systems exist naturally, so we expect for them to exist. Having said that, if their amplitude starts becoming such that causes the tripping of units, this is where I think the problematic situations start. So hopefully we will not see the effect of them, to put it that way. Even if we don't observe them, we will not see trips related to, if you have a voltage oscillation that goes to 1.2 per unit for 2 or 300 milliseconds, then a converter can trip because that goes outside of the normal operating condition. More than 20% for a set amount of time, protection devices usually will trip the unit. Depending on grid codes, of course, different countries have slightly different exact numbers, but the idea is the same. So this is one of the worries there. That's why we also came up with this variability perspective, because this is what exactly we're trying to capture, this effect of the magnitude of the oscillation and how long does it withstand and so on. So definitely we would need more monitoring. If you're asking me, I would invest in that. But yeah, there's an element of if you have the monitoring, then you see them, then you have to do something about them. So it's a bit of a challenging
Yeah.
situation.
So there might be lots of like unrecognized oscillations already in some areas. I don't know.
Possibly,
Yeah,
possibly.
possibly. Yeah, anyway, yeah. Thank you for your clarification. And also, I think the time is almost running out. Oh, let me introduce the next webinar from now. So everyone, the next webinar will be held next month, specifically the July the 14th at 1 p.m. our time. And we're going to invite a scholar from Spain to showcase European hybrid converter project named iPlug. And then the flyer will be uploaded to the IEEE section website in a day or two. So please stay tuned and then enjoy the rest of your day. And then also, again, Panos, thank you for the nice presentation. I really appreciate it.
Well, thank you very much for the invitation, and thanks to everyone for interacting, for staying here and listening, and for the comments as well. So thank you very much again, Koji.
Yeah.
And looking forward to see you two in general
Yes.
meeting
Yeah.
in
See
a
you
while.
in Texas. Yeah. So yeah,
Very
please
good.
send me the slides if you have time.
I will do that. Yes, I will do
Yeah.
that.
Thank you for
Thanks a
very
lot
much.
again.
Yeah.
Thank you,
So
everyone.
bye for now, everyone.